We're about to delve into Florida rainfall characteristics, a topic developed by Harvey H. Harper. Our primary aim is to improve your understanding of rain and its variability across the state. This knowledge is crucial because rainfall is the driving force behind runoff and the pollutant mass it carries. In this module, we'll focus on precipitation and its fundamental role in driving the hydrologic cycle. Precipitation essentially controls runoff, making it a critical factor in how we manage water resources. When precipitation occurs, the resulting runoff component needs to be both conveyed and treated, especially in developed areas. Therefore, a thorough understanding of precipitation is absolutely essential for accurately understanding and quantifying runoff volumes. We'll be working with the basic hydrologic equation, which states that rainfall equals runoff plus infiltration plus evapotranspiration. This equation helps us describe the management of runoff and infiltration, and the changes water undergoes in its various states. Specifically for Florida, this module will help you understand the changes in water volume and the concept of inter-event dry periods, which are crucial for our local conditions. Ultimately, a solid grasp of precipitation will enable more accurate calculations for annual quality impacts related to water management. Given that rainfall is the primary driver of the hydrologic cycle, the Harper 2007 study meticulously evaluated various rainfall characteristics across Florida. This included looking at both annual and individual event rainfall depths, as well as the overall variability of rainfall throughout the state and across different individual events. A critical aspect of this evaluation involved understanding inter-event dry periods. This is a crucial concept because it represents the specific time allotted for treatment processes to occur without any additional rainfall input. For example, in the context of stormwater management, it's the time available for infiltration in retention basins. The longer this inter-event dry period, the more effectively a particular volume of runoff can be treated. By simulating all rainfall events and carefully considering these inter-event dry periods, researchers can estimate the percentage of runoff that can be treated over an entire year. If an inter-event dry period isn't quite long enough to treat all of the runoff from a previous event, then a fraction of the storage capacity remains available for the next runoff event, which is an important consideration for system design. Ultimately, understanding this variability across the state and throughout the year is key to designing effective water management strategies. To understand how rainfall affects runoff, we downloaded extensive historical meteorological data for each site. This dataset spans a 30-year period, from 1971 to 2000, and includes information from 111 individual recording stations located throughout Florida. From this data, we specifically evaluated the annual rainfall depths, which refers to the total volume of rain, and analyzed the variability of that rainfall across the state. The primary purpose of this detailed analysis was to accurately characterize the annual rainfall patterns in Florida. We're looking at the average annual rainfall for Florida, specifically data developed for the period between 1971 and 2000, based on historical records. These are represented by what we call rainfall isopleths, which are lines connecting points of equal rainfall depth. These maps are incredibly important as they're used to determine the project rainfall for water management district permits, and are also integrated into tools like BMPFast for best management practice assessments. Florida's rainfall is quite variable across the state. The average annual volumes range from a low of about 38 inches in the Florida Keys, all the way up to around 68 inches per year in the Panhandle, particularly west of Tallahassee. This dataset, which covers the 1971 to 2000 period, was developed by Harper in 2007 and is commonly referred to as the 2000 data. We are now looking at the revised 2024 rainfall contour map. The Florida Department of Environmental Protection, or FDEP, developed this updated annual rainfall map by utilizing data collected from 1990 through 2024, which is now referred to as the 2024 Annual Data Set. This new data was published in the Applicant's Handbook, Volume 1. When comparing this 2024 data to the previous 2000 data set, we observe that while there are some regional differences, many areas show very little change. For instance, some of the observations include slightly lower rainfall values recorded in the Panhandle region, contrasted with slightly higher values in the Tampa Bay area. The variability in the 2024 data set ranges from a low of 41.6 inches in the Florida Keys to about 66.70 inches in the Western Panhandle. This is comparable to the 2000 data, which ranged from approximately 38 inches in the Keys to a high of about 66 inches in the Western Panhandle. Moving forward, permit submitters and reviewers should primarily use this 2024 data set, unless more specific local rainfall data is readily available. Both of these data sources are also integrated for use within the BMPFast tool. For our meteorological evaluation, we began by obtaining historical 1-hour rainfall data from the National Climatic Data Center, or NCDC. We were able to gather this data for 45 out of 111 available meteorological stations across Florida. The data availability for these sites varied significantly, ranging anywhere from 25 to 59 years per location. A crucial step in our analysis was to group this continuous rainfall data into individual rain events. To define what constituted a distinct event, we used a 3-hour separation period. This means if there was a dry period of at least 3 hours, we considered the subsequent rainfall to be a new independent event. This methodology aligns with research, such as that by Evangelista in 1978, which indicates that a 3-hour inter-event dry period is generally sufficient to establish the independence of rainfall events. This process allowed us to create a comprehensive historical data set of daily rain events for each monitoring site, spanning its entire period of record. By doing so, we could analyze the variability within individual events and, importantly, characterize the inter-event dry periods. Ultimately, this enabled us to develop a frequency distribution of individual rain events for each monitoring site, providing valuable insights into local rainfall patterns. To evaluate meteorological variability, we first obtained historical 1-hour rainfall data from the National Climatic Data Center, or NCDC. We carefully selected 11 meteorological stations, each providing robust hourly data. The availability of this data varied significantly, ranging from 25 to 59 years per site, with a strong majority, specifically 9 out of the 11 stations, possessing 45 years or more of continuous records. A crucial step in our analysis was grouping this raw data into individual rain events. We employed variable criteria for defining these events. For smaller events, those equal to or less than 0.25 inches of rainfall, we defined individual events based on a 3-hour separation period. For larger events exceeding 0.25 inches, we used a 6-hour separation to ensure we captured distinct rainfall occurrences. This meticulous grouping allowed us to create a comprehensive historical data set of daily rain events, spanning the entire period of record for each selected site. From this, we then developed annual frequency distributions of individual rain events for every monitoring location. It's important to note that the annual rainfall volume frequency distribution curves were initially developed by Harper, and these results have been both published and thoroughly reviewed. Prior to this, Evangelista published work in 1978 focusing on percent capture for recovery times of no more than 3 hours. Harper later extended this in 2007, providing insights for recovery times up to 72 hours. These foundational studies are critical, and Harper's removal tables are in fact published in the Applicant's Handbook, Volume 1, dated June 28, 2024. This graph displays a typical rainfall event frequency distribution. What we observe here is that the vast majority of individual rain events are relatively small in magnitude. Specifically, more than 50% of independent rainfall events measure less than half an inch. Expanding on that, approximately 90% of these events are less than 1 inch in depth. Conversely, only a relatively small number of annual events result in a large depth of rainfall. This pattern is generally consistent across various stations throughout Florida, though with some localized variability. This understanding is critical for water management, as it indicates that a large fraction of the annual runoff can be effectively managed by focusing on these lower rainfall volumes. This approach contrasts with the strategies used for larger rainfall events, which typically focus on managing high runoff rates for flood control. We're examining the characteristics of rainfall events at selected meteorological sites across Florida. What's evident is that Florida rainfall is highly variable, both in the total number of events and the distribution of small versus large rainfall occurrences. This variability in rainfall depth has a significant impact, influencing both the amount of runoff generated and the overall efficiency of our water treatment systems. For example, the sheer number of rainfall events in a year can differ quite a bit across the state. We observe a high in the Miami area, which experiences about 158 events annually, contrasted with a much lower figure of around 104 events in the Cross City area in Dixie County. Beyond just the frequency, the characteristics of these events also vary. We find that the percentage of annual events with rainfall less than 1 inch ranges from a low of about 84% to a high of nearly 94%, specifically 93.5%. This considerable variability in both the number and size of rainfall events is crucial for understanding why the percentage of annual discharge that can be effectively treated also varies so significantly across different regions of Florida. The inter-event dry period, which is the time between rainfall events, exhibits significant variability not only across different regions of the state but also seasonally, shifting between wet and dry periods. This natural variability in rainfall frequency has crucial impacts on how we manage stormwater. Firstly, it directly affects annual runoff coefficient, or ROC, values, causing them to vary significantly. This makes it challenging to predict runoff volumes accurately without considering these fluctuations. Secondly, and critically, the recovery and overall performance efficiency of stormwater management systems are profoundly impacted, especially those relying on retention. These systems require sufficient dry periods to restore their storage capacity and optimize their treatment processes. If dry periods are shorter or less predictable, a system may not fully recover before the next rainfall event, leading to reduced effectiveness. To accurately design and evaluate these systems, it's essential to account for these variabilities. This often necessitates conducting simulations to determine the appropriate recovery times and predict the overall performance of a treatment system under various inter-event dry period scenarios, much like the diverse data you see here, which reflect this inherent variability. We've learned that rainfall in Florida is remarkably variable across the state. This variability isn't just about the total annual volume, but also the number of rain events. For instance, annual rainfall can range significantly, from about 38 to 42 inches per year in Key West, all the way up to 66 to 68 inches per year in the Panhandle area, west of Tallahassee to Pensacola. The number of annual rain events also varies considerably. We see a low of around 104 events per year in Cross City, but this number can go up to 158 events per year in Miami when considering a 3-hour independence between events. Interestingly, most individual rain events in Florida are quite small, typically less than half an inch. In fact, approximately 84 to 94% of all rain events are less than 1 inch deep. There's also variability in the inter-event dry periods, particularly during the wet season. These dry periods can range from about 1.42 days, or 34 hours, to 2.27 days, which is about 54 hours. All this natural variability in rainfall, whether it's volume, frequency, or dry periods, directly impacts runoff volumes and consequently the effectiveness and performance of best management practices, or BMPs, throughout the state, as their design often relies on specific treatment times for runoff. Thank you for viewing this presentation on Florida rainfall characteristics, prepared by Harvey H. Harper. We encourage you to proceed to the other learning modules to understand more details related to stormwater management for water quality improvement. This concludes our presentation.